Get back to work here. So, I will say this, that the fried cheeseburger at Logan's is notable. Have you guys ever had that? It's like a cheeseburger with a piece of fried cheese on top. It's like it's very cheesy. Maybe too cheesy. I don't know if that even makes sense, but all right. So let me talk about the solution here right quick. And of course, I just wrote this, so if there's a mistake, let me know. I'll take points off my quiz. Okay, so to start with, to solve problem 1, we square both sides because the radical's already isolated. So squaring both sides is the thing you want to do to get started. And then, once I do that, well, I have to multiply it out. So when I multiply this out, when I FOIL that out, I get a 6 times 6, which is 36. Square root of x times the square root of x, which is x. And then I get 6 root x, and then I get another 6 root x from multiplying it out, which gives me a 12 root x over here. On the other side, 2 squared is 4, and the square root of x plus 9 squared is just x plus 9. Multiplying that out gives me 4x plus 36, but you notice I've got a 36 over here as well, so they cancel. Solving for 12 root x gives me, see this x minus 4x gives me 3x. Then I divided by what? Oh yeah, I divided by 12, and then 3 over 12 is 1 over 4. And then I squared both sides, which gave me x over x is equal to x squared over 16. Which then I thought, why am I looking at a fraction? This is crazy. So I put the 16 on the other side and flipped it over to confuse the students. Mission accomplished, right? And then I factored, because this is x squared minus 16x, which is x times x minus 16. And so either x is equal to 0 or x is equal to 16. I was kind of expecting one of these or the other to be extraneous, but they actually both work. So because I was like, well, plug 0 in, it's going to be extraneous. And then I'm like, wait a minute. 6 plus 0 is equal to 2 times the square root of 9. But 2 times 3 is 6. So yay. It so happens that both of the solutions work in this case. Like a lot of the problems we worked in the past, there's been one or the other which were extraneous, right? But not for this one. Anybody get this? What's that? A third credit? Okay. Well, if you didn't get it yet, work on the problems from that section, right? I see some yesing, so that's good. So the natural enemy of the 3/4 power is the 4/3 power. So take both sides, exponentiate them to the 4/3 power. Doing that gives me just 2x minus 1 on the left-hand side. On the right-hand side, I get 8 to the 4/3 power, which is really 8 to the 1/3 power to the 4th power, which is really 2 to the 4th power, which is otherwise known as 16, which then solves for 17/2. So, question? No? Okay. So, problem 3. Problem 3 here. I have, I mean, there's various ways of doing the steps, but after you simplify it down, I got to x to the minus 1/2, y to the minus 3/2, which means a is negative 1/2 and b is negative 3/2. So.
Wouldn't 1/2 minus 2 be negative 1/2?
Which one? Are you? What
So
are
it would be
this one?
1/2 minus 2 is negative 1.5, right? Not negative 3. Oh, that's the same. Okay, my bad.
Are you using mixed fractions in my class?
I'm so sorry.
How dare you? We don't speak of 1 and 1/2. Only 3/2 for us here. But anyway, sorry, as we've discussed, I have a hatred of improper fraction. I mean, of mixed fractions. I'm sorry, I forgot to erase that. Oh well. So 2/3 less than 2 is less than or equal to 1 is less than or equal to 3. That means we're in case 1. So I plug the 2 into that formula, I get 19. Because 3 times 4 is 12. 12 plus 7 is 19. On the other hand, 4 is larger than 3, which puts me in case 2. So to calculate f of 4, I use case 2. 2 minus 4 to the 3rd power, also known as 2 minus 64, is minus 62. So that's all there is. I hope somebody got this one. You got that one? Good. If you missed this problem, figure out why you missed it and fix that, right? Because this is not a big deal. This problem is on the test. If I ask this problem, like, everybody should get this one right. This is not a hard problem at all, right? This is just read the instructions, right? This is a case-wise defined function which says you have to read the instructions. The instructions are x less than or equal to 3, you use this formula. X greater than 3, you use that formula. Yeah.
Is case-wise and piecewise the same?
Case-wise and piecewise, yeah, that's kind of the same animal. Piecewise is like another word used for case-wise. I think those are pretty much synonymous. And let's see, this one here, this pesky dot right here, was supposed to indicate to you that f of minus 2 is equal to 4. Now, if you didn't get that, no shame in that. I haven't really talked about this I didn't quite talk about this. I kind of talked about it in terms of the dot being filled in, indicating the point was in the graph, but I didn't talk about a dot on its lonesome, right? So now we've talked about it. This is a possibility. You can just draw a dot, and that indicates that that point is in the graph, and that means that f of minus 2 is 4. Now, if that dot was not there, then what? F of minus 2 would be what? Does not exist, right? Yeah, because the open circle down here. The domain, there's an x value in the graph from minus 6 all the way over to 4. 4 is not included, so I have to omit that. And then it starts again. It goes from 4 all the way over to 8. 8 is included because of the solid dot there, but that's the domain. All right, so basically the domain is everything from minus 6 to 8 except for 4 in a sentence. And in the range, well, let's see, we go from y value minus 4 all the way up here to y value 6. Now the 6 is included by that dot, right? But minus 4 is never attained anywhere in the graph. So it's minus 4 not included to 6. So I hope some of you got that. If you didn't, think about why you didn't get it and try to adjust, all right? So are we good? Okay, so I don't always have time to go over the solutions to the quizzes in class, but today we did, so here it is. Now, while I've got this out, let's play some games. What? Math games? Well, of course. What other kind is there? Let's see here. Show of hand. Who in here plays Fortnite?
Like actively or how?
No, actively. Huh. Interesting.
Why do you?
No, not really. But my children do. Well, I'm planning to start. Listen, guys. Desmos.com is a free website that basically do graphing calculator, right? It's a free graphing calculator. I think you can get an app which does this as well. I haven't looked into that really, but who uses apps anyway? I mean, you have a web browser on your phone, right? So you can just do that. www.desmos.com. Okay, so let's look at a graph that we know. Y equals x squared. Here we go. It is, as you can see, a what? A parabola, right. And what would happen if I add a constant like this? See, one of the excellent things about Desmos is if you add a letter, it allows you to put it in as a slider. And then you can adjust the thing by just doing this little up and down like this. And you can even do this. So what it's doing right now is it's animating what happens to the graph, right, for different choices of the, oh cool, you got it. For different choices of the adding the constant, right? So the thing I want you guys to see from this is that if we add a constant to the graph, what's it do to the graph? Actually, let me add another picture in here. Let's add another picture, right? let's add in as a reference point the basic graph. Here's the basic graph of y equals x squared, all right? So it's in green, and let's see here. If we add a positive number, what happens? What happens to the graph? If we add a positive number, it takes the given graph and it does what? It shifts it up, right? So adding a number to a graph just vertically translates the graph, right? If I subtract, what happens? Oh man. If I do like subtraction, it does what? It shifts it down. So, all right, that's one thing we can do. Now let's look at a different thing. What happens if instead we look at y equals to, let's say, x plus c? Not plus, I want to do c there. Let's do plus b, all right? Squared. I'm going to turn off the other graph. All right, so here is what happens if we add, see the difference? So I'm replacing x. I'm replacing x with x plus 3.1. What happened to the graph? The original's in green, the one's in blue. What happened? It translated it 3.1 units to the left. Do you see that? Adding a number inside the argument of the square moves it the other way. If I make the b negative, watch what happens. Now, if you think about this for a second, it makes perfect sense, right? What is x minus 4 squared? It's the parabola that has the vertex at 4, 0, and it bounces up, right? We know that, right? So, but the larger point here is if we take x and replace it with x minus a constant, it has the effect of shifting the graph to the right. Let's try this with a different function. What happens if we study like y equals square root of x? All right, and first of all, we know what's going to happen if we do plus c, right? Let me turn off the other graph. So and let me add a reference graph. All right, so there's my my reference graph in blue in this time. And see what happens if I move c? If I add a number to the square root, it shifts the square root graph up, right? And what happens if I subtract? It shifts it down. What happens if I do both at once? What if I do x and let's do plus b? Now what happens? What happens if I do both at the same time? Let me zoom out a bit. So you see what's happening is you can move the square root graph left, right, or up or down by controlling the values of c and b. See that? Let me focus here on a specific case. Like if I freeze b to be, minus 5-ish. I'm trying to get it to 5. It's hard. It's fussy. Come on. Too far. Stupid mouse. All right, good enough. And if I shift c to be plus 5, see what happens? So subtracting 5 inside the square root shifts it 5 to the right. Adding 5 shifts it 5 up. If I make the constant I'm adding outside equal to 1, it shifts it down, right? If I make the constant I'm adding outside, stop that, negative, then it goes down like that, right? So I hope you're starting to see you start to see the patterns of what happens if we add a constant to the formula. It takes the graph you're given and either shifts it up if the constant's positive or shifts it down if it's negative. On the other hand, if we replace the argument with x minus a constant, then that moves it to the right, if that constant's positive, let's say. Here's another one. Let's say 1 over x. You guys ever seen the 1 over x graph? Here it is. There's y equals 1 over x. What is this, actually? What is this graph? It has a name. We've talked about it. It's a hyperbola. But it's not a hyperbola of the form we're used to, right? Here you're looking at a hyperbola which is rotated 45 degrees. So like the asymptotes for this hyperbola are actually the x and y axes. So it doesn't fit into the formula that we had to deal with for last test. But check this out. If I do y equals 1 divided by, let's say, x minus b, see what happens. If we make b positive 1.3, see where it is? It's shifting it to the right if b is positive. Now, if b is negative, what happens? The transform graph goes to the left, right? So, all right. Well, anyway, let me stop playing with this and just write down our observations in a theorem, okay? So, there was one other thing. Oh man, look at that. One other thing. What happens if we say multiply? What happens if you multiply like y equals, c times x squared? What's that do? So the multiplied graph is in black. Do you see what happened here? So the number I'm multiplying at c is minus 5 at the moment. Let me animate it. Let's look at what happens. So there c is positive, c is negative. Positive, negative. And right in the middle, 0, right? If we multiply by 0, we just get the 0 graph, which is the x-axis, right? Y equals 0 is the x-axis. So that's in between these two. But the effect of multiplying a graph by a number is it stretches the graph out, right? It stretches it out. And if you're multiplying by a negative number, what does it do? It flips it over, right? So multiplying your formula by negative flips it over the x-axis. One other thing. How about what happens if we do like y equals the square root of cx? What's that going to do? Let me use a different letter so I can have control of it. I'll do m, add slider m. Okay. Let me turn off these other graphs, I'll turn this one back on so we have a reference point. So there we're looking at, let me turn that one off. All right. Okay, so where did my square root x gone to? They're the same one, aren't they? So you can't see it, right? What happens if I shift this a little bit here? So the blue one, wait a minute, no, the blue, so I'm multiplying by, so that the x, now there's a couple different ways you could look at this, right? Think about this. We have y equals the square root of mx, right? There's two different ways to look at this. The one is that you're replacing x by, okay, so we could look at f of x equals the square root of x, right? So one way to look at this is that this is equal to f of mx, all right? That's one way you could look at it. The other way you could look at this is it's the square root of m times the square root of x, right? Which is the square root of m times f of x. So this actually gives us an example of both adjusting the domain and also the range by a number. And so if we're looking here at m equal to, let me make it more specific. If we look at m equal to 4, right? Let's focus on this one here. The one way to look at it is we're stretching it vertically by a factor of 2. All right, so like this point in the original graph was 1. In the multiplied graph, it's 2. This one was originally like 1.414. In the multiplied graph, it's 2.8. All right? So we're stretching it vertically by a factor of 2. That's what this way of looking at it is. All right? M times square root of m times f of x. But the other way you could understand it is it's smushing the graph. It's compressing it horizontally. See this? Check this out. So this point was originally at 2, right? And where is it now? It's all the way over here, isn't it? let's see here, if I can find another one. So this one is actually, I got to be more specific. This point here is originally at 4. Where is it? Where does this point go to on the transform graph? Not 4, actually, all the way down to 1, right? So what I'm saying is you can either look at this as this. So for us, it's either 4 times f of x, right? Or it's f of 4x. See, it's different. My bad. What's the square root of 4? 2. All right. So for this one, you can either look at what's going on as stretching vertically by a factor of 2 or compressing horizontally by a factor of 4. See, because like this point, which was originally at 4, is now in the new graph over here, right? And this one, that one was originally on square root of x at 1, 1. In the compressed graph, it's over here at 1/4, 1. So these are two competing viewpoints. You can either, for this example, you could either view it in terms of stretching the square root vertically by a factor of 2, or you could view it as compressing horizontally by a factor of 4. All right. What happens if you make m negative? Look at that. I made m negative. What happened? The transformed graph now, the domain is negative numbers, right? Because if you look, what's the domain of f of x, say f of, g of x equals the square root of minus 4x. What's the domain of that? See, the domain of this is when minus 4x is greater than or equal to 0. That makes x necessarily non-positive, right? It has to be either negative or 0, and that's what we see in the graph over here, right? But again, since I'm multiplying by minus 4, the input, it corresponds to, well, there's two things that's going on. The one thing is replacing x with minus x, flip the graph over the y-axis like this, and the other is that it compressed it by a factor of 4. So these are the different transformations of graphs. Let me write them out on the board here. All right, so here's the deal. Given y equals f of x, all right, we may construct new graphs from old via, and so let me do the formula and a description over here, and let's catalog what we just saw, all right? So if the formula is y equals to f of x plus some constant c, and listen, in the interest of not in being clear, let us assume, we're going to assume that c is positive for the sake of this discussion, all right? So I'm gonna assume c is positive, and I'm going to write down pluses and minuses so I can separate like left and right and up and down cases, all right? So f of x plus c, this means, shift up, right? Shift up c units. If I do y equals f of x minus c, what happens? Down, right? Down c units. Down by c. So it's a shift down by c. On the other hand, if we have y equals f of x minus c, this is shift right by c. If we have y equals f of x plus c, that's a shift left by c. If we have y equals c times f of x, this is a vertical stretch by c. If we have y equals to f of c divided, x divided by c rather, this is a horizontal compression by c. And then finally, two more. If we have y equals to minus f of x, this flips over x-axis. If we have y equals to f of minus x, this flips over y-axis. These are the transformations of graphs that are basic. And so what this means is that if we have a basic catalog of graphs that we know, we can start with one of our basic graphs, and then we can apply these transformations to create new graphs. So what are our basic graphs? So you've got, like, for example, y equals x squared, y equals the square root of x, y equals 1 over x, y equals 1 over x squared, y equals, mx plus b, y equals the cube root of x, y equals the absolute value of x. These are all basic graphs that we should know. Y equals x cubed is another one that these are graphs that you really should know by heart for this course. And I don't mean that, what I mean is you should have a general sense of what they look like without looking in a book or consulting a graphing calculator or anything like that. You should be able to just kind of write them out. So here's a quick sketch. The first one looks like this. The second one is like half of a parabola. The third one is, we just looked at it, it looks like this. The fourth one is the volcano function. Let's see, let me number them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 5 is a what? What's 5? You guys can tell me that. You guys already know this one, right? That's a line. So it's like this, right? 6. This may be unfamiliar. This is something you may need to learn right now, but the graph of the cube root function looks like this. All right. The absolute value function, it's a v. And the cube function is like that. So, example. If I was going to graph y equals 1 over x minus 1 squared plus 2, the way I would do that is I would start with the volcano function, which is this. And then I look at this. What is this formula? What's this formula saying? It's saying shift right by 1, then up 2. So basically the graph is going to be, so the vertical asymptote is kind of the key feature there. So the vertical asymptote moves to x equals to 1, where it was at 0 here. And there's a horizontal asymptote at y equal to 0, and that shifts up 2. So the graph of the shifted volcano function, it looks something like this. I didn't have to plug in a single point, right? Like, the idea is that you know the basic functions, and then you can move them around with these shifts. Let me do another. Example 2. suppose you want to graph 2 plus the square root of, let's say 3 minus, well, let's just say 2 plus the square root of minus x. Right? So I start with thinking about this is square root. And then I'm like, this is y equals square root of minus x. All right? And then what? I have a plus 2, right? So then I do shift up by 2. So there you go. That's y equals 2 plus the square root of minus x. Now, I don't think that I just glanced over your homework before I was teaching today. And I don't see in your mission 2 that I've really given you guys any problems which force this upon you. I don't think, I have to double check again, but you know, sometimes there are problems which force you to use transformation of graphing to create graphs. So I don't think I forced this. This is really for you guys, just another way you can think about how to graph things. But this is very useful, and it will save you a lot of time if you can see the graph that you're asked to make as a simple translation of one that you already know. And this is more important though. You do need to memorize these if you don't know these yet. Like you need to get these kind of in your system. Or hey, wait a minute, you guys get a formula sheet, right? So these deserve a spot on your formula sheet for test 2 for sure. Anyway, I think that's about it for today. Next time we'll do operations of functions and stuff like that. So let me